Hello everybody, our new unit is about solutions. We're going to start by learning some of the calculations that you'll do to come up with the concentration for various solutions. So just a reminder, because it has been a while since Honors Chem, that a solution is considered a homogeneous mixture. So it's something that is mixed uniformly. One part does not seem different than the other. Not everything is a solution, but a homogeneous mixture is what we're talking about here. Some definitions that are important because they're going to show up in our calculations and our equations are solute and solvent. So the solute is the stuff that you're dumping into the solvent. So for example, the salt that's inside salt water would be the solute. That was the part that was dissolved in the water. Sugar inside a soda would be a solute. They're not always solids that are being dissolved. So for example, in a soda, you have carbon dioxide. You can have gas be the solute that's dissolved inside the solvent. In our saltwater example, water would be the solvent, and in our soda example, water would be the solvent. They dissolved a bunch of stuff into water to make the soda. Identifying which substance is the solute and the solvent is important because we will use things like their masses or their volumes to perform our calculations. This is probably the most commonly used concentration unit in our chemistry class, molarity. How many moles of solute are in 1 liter of solution? The reason we really like this calculation is because it has moles in there, right? And we are always trying to convert things to moles. And from a practical standpoint, when I mix up solutions to go store in the stockroom, I use 1 liter jugs. My bottles that I use that I put on the shelves are liter sized. So I can figure out how many moles do I have to put in the container, and then I fill it up with water to make a liter of my solution. And so molarity is a very common one that we use. For example, if you had a sugar solution that was 2 molar concentration, 1 liter of that would have 2 moles of sugar inside. So if you had 2 liters, you'd have 4 moles. If you had half a liter, you would have 1 mole. So we can do a lot of calculations to convert from a volume. I can measure it out in my graduated cylinder, and I will be able to figure out how many moles of solute is in that container. Here's one that sounds very similar that does not get used often, but it does pop up once in a while, so it is important. It's called molality. So molality is similar. We have moles of solute. That part looks the same. But if you look at the bottom, it's a little different. It's not liters, it's kilograms. And it's not solution, it's the solvent. I see more mistakes with this one, I think, than any other, because most of our calculations care about the solution volume once it's all mixed together, right? Once it is a solution, once it is a mixture. This one has mass of solvent, so it's a little bit strange. This one is important because it's not going to vary with temperature. So some branches of science and some types of reactions and some topics within chemistry prefer molality because if you change the temperature, the volume won't change and therefore the concentration doesn't change. So it can be very useful. We won't use it very often. you'll notice it's a lowercase m. So be a little bit careful. We're used to using lowercase m in different ways, right? So the context of the problem is important to know what unit you're looking at. There are lots of ways to get concentrations based on what are called parts. So it's how much of your solute and how much of your solution. We say the part solute, part solution. You can use masses or volumes. Usually you would do things with the same unit. So you would say how many grams of solute in how many grams of solution, or how many kilograms of solute and how many kilograms of solution. Or maybe it's by volume. So how many liters of solute in liters of solution. So we see this when we're talking about percentages a lot, percent by mass. You can see here 0.9 grams of solute in 100 grams of solution. So we're looking at what part of it is solute and what part of it is the solution. When you take classes like environmental science classes, you may hear things like parts per million. So what parts per million is how many parts of solute do you have per 1 million parts of solution. So how many milliliters of solute in 1 million milliliters of solution, for example. The reason they're using such a big denominator, the reason they're using so much solution, is because things like pollution, right? Usually it's not very much present. And so it's such a tiny number that they use this parts per million. Mass percent can be very common to see, like on the previous slide. Make sure you multiply by 100, right? Here's your parts per million. Now, one of the things that I notice is that people forget how to multiply by 1 million. You can either do 10 to the 6 or just count out your zeros, right? 1, 0, 0, 0, 0, 0, 0. Just make sure in your calculator you count carefully. So you're not going to often see this type of a calculation unless it's something that has a very, very low concentration, like pollution, for example. Another thing that is incredibly important that you do need to memorize is the density of water, because that will help you figure out how much your solution or your solvent would weigh. So remember that 1 gram weighs 1 milliliter, which is the same as a centimeter cubed. It would fill a 1 centimeter by 1 centimeter by 1 centimeter box. So this bottom stuff here in the corner, make sure you remember that or you're going to get stuck on a lot of these. They will not tell you what the density of water is. Now, let's say that you have a really, really small concentration. You might even see parts per billion. That's 10 to the 9. So all of these parts per calculation are basically the same. Some amount of solute over some amount of solution times some factor. If it's a percent, we times it by 100. If it's parts per million, we times it by 1 million. If it's parts per billion, we times it by 1 billion. So kind of moving on, the next common thing you might see is what's called mole fraction. You've learned mole fraction in honors chem. We've used it in a variety of ways. you're going to take the moles of something you're interested in divided by the total number of moles on the bottom. If you have 2 things, you add up both. If you have 3 things, you add up all 3. If you have 4 things, you add up all 4. One thing to notice is that it doesn't have units, right? They're going to cancel out. And if we added up all our mole fractions, they would all add to 1. If you want, you could times it by 100, and instead of a mole fraction, now it's a mole percentage. And instead of adding up to 1, it would add up to 100. Remember, with your rounding, sometimes maybe it's not quite 100%, but it should be close enough that you feel comfortable with your answers. Now, you can find charts with all different types of calculations, all different units of concentration. I'm not going to sit here and put into the lecture every single possible one I could ever possibly think of. I went over the most common ones that we tend to see, and if I were you, I would maybe keep a little cheat sheet, and anytime you stumble across a concentration unit or a manipulation of numbers that maybe is more unique, I would write it on your cheat sheet. And then that way, right, you have something to study off of as you come across the variety of worksheet problems that you'll practice. People often get really stressed out on this chapter because the problems will often not give you very many numbers. And you feel like you don't have enough because you have to find a creative way to manipulate them. Or they'll give you so many numbers and half of them aren't even necessary. It's extra information. And people sometimes have a hard time seeing the pathway to get from one unit to the other. Kind of like when we started doing dimensional analysis. Some people struggled with knowing what step to take in what order. And it does require practice. It requires repetition. You need a little bit of muscle memory so that your brain can leapfrog from one unit to the other and one conversion to the other. So just some suggestions for if you're feeling a bit overwhelmed or a bit stuck on what path to take is I cannot stress more that you need to write your units out. This is about converting units. And if it's about converting units and you don't write units on your paper, you're already going to have an uphill battle, right? When you see the units written on your paper, it gives your brain a visual to lock onto and you will probably have an easier time. Now, a lot of our concentration units like molarity will be written as a single letter like a capital M. And while you may know that molarity is moles per liter, I have found if you take the time to actually write that out, instead of a capital M, write moles per liter, that will help you figure out the pieces of information you already have and which parts you can convert. And once you write it as the ratio, once you have all of your info written as a ratio, you can separate it into the numerator and the denominator, and you can think about each part separately. Because one of those numbers will tell you info about the solute, and one of those will tell you about the solution, typically. Maybe the solvent, right? But usually the solution. And when you see them written separately, as a numerator and a denominator with their units attached, you can then convert each piece separately. And then you can combine those pieces back together to get your final answer. And I have noticed over the years, students tend to have more success when they go through this thought process of separating into numerator, denominators, solute, solvent, and actually writing those units out. So I have a few practice problems for you. Remember, you can pause the video to give them a try and then unpause when you're ready to see the answer. For the first one, please find the mass percent of copper sulfate in a solution whose density is 1.3 grams per milliliter and the molarity is 4.73 molar. If you just looked at all those random numbers, you may not see how they connect. But if you think about the equation for mass percent and the units that you're after, and then write your molarity as moles per liter, right? Think of it that way. You should be able to figure out places you can plug in and do some conversions to get mass percent. So pause and see if you can puzzle through that. See if you can kind of figure out all the little pieces and how to put them together. All right, how did you do? 58.1%. So when I look at this, I think to myself, okay, 4.73 molar means that 1 liter of solution will contain 4.73 moles. So now I know something about the copper sulfate, which is my solute. I know how many moles there are. And if I know how many moles there are, I can do a molar conversion to get to grams using molar mass. 1 mole of copper sulfate weighs 159 grams. So in a 1 liter jug, I know that 755 grams of it will be copper sulfate. That's my solute. I just figured out the top number, didn't I, for my mass percent. Now I have to think about the grams of solution. It's not the grams of solvent, right? It's not a liter of water. It's a liter of water mixed with the copper sulfate. You notice they gave me the density of my solution. Well, if I have a liter of solution, I could take that and use my density to convert to grams. So a 1 liter jug of this solution would weigh 1,300 grams. Well, now I have the grams of solute and now I have the grams of solution, so I can divide them, multiply by 100, and I find out that by mass, 58.15% of this bottle would be copper sulfate. Now at this point, people often say, but it didn't tell me I had a liter. How do I know to start with a liter? Well, you could have started with anything, but picking 1 liter makes our life so much easier, doesn't it? It saves us conversions. Because if I assume that I have a liter of solution, this molarity up here becomes this direct relationship, makes it super easy to start with 4.37. Now, if you started with 17 milliliters, then you're going to have to do more calculations, aren't you? More conversions. So starting with a liter really makes that simple. If you remember back to when you were learning about empirical formulas and molecular formulas and combustion analysis, didn't we often pick 100 grams to do our calculations with to make our life easier? That's what we're doing here. We're picking 1 liter of solution to make our life easier. It doesn't matter what volume I have. It would always have the same answer. It would always have the same percentage, but 1 liter will make my life easier. All right, let's try another one. What's the mole percent of ethanol when there's 71 grams of ethanol for every 14.3 grams of water? So you have grams for both, and you're trying to get to moles, and you already know how to do that, don't you? You know how to go grams to moles. So pause the video and give it a try. All right, now one thing that people will sometimes ask is how do you know which thing is the solute and which thing is the solvent? And water is typically your solvent, right? So that's kind of nice. Sometimes if it's something you're not used to, look for the phases. If they tell you one's a solid and one's a liquid, right? Usually you can go with your liquid being your solvent. Here, if you notice, they asked for mole percent of ethanol. That tells you that's the top part because that's your solute. If they're asking for the percent of something, put that number on the top. That's your A value. And you see here we're finding mole fraction of A. So that's another thing you can look for is the phrasing of the question. So let's take 71 grams of ethanol. Let's use the molar mass. And we will convert and find out how many moles we have. Now let's convert grams of water into moles of water. And because we're interested in the percent of ethanol, that's going to go on the top. And it's the sum of the both numbers on the bottom, right? So I'm going to add those together. And I get my final answer. Okay, one more. Let's practice that weird one that we don't use super often, molality. What's the molality of a solution of propanol mixed with water? It told you how many grams of propanol you're going to use, and it told you a volume of water. So you're going to have to convert from grams of solute to moles of solute. And you will have to convert from milliliters of water all the way into kilograms of solvent. So milliliters to grams and grams to kilograms. Be careful with your decimal points. I see a lot of people trying to do these grams to kilograms or milliliters to liter conversions in their heads, and they will often make mistakes and they'll be off by a decimal point. So be a little bit careful. All right, pause the video and give it a try. Right, there's your answer, lowercase m. Let's take our grams and use molar mass of propanol. Now we know how many moles of solute we have. Now, if I have 152 milliliters, that's 152 grams, which is the same as 0.152 kilograms. Now, I didn't show that on my paper, but if you need to do your metric conversions on your paper, if you need to do it with dimensional analysis or you need to do King Henry and move your decimal, you do what you need to get it right. We get our final answer. Okay. Let's do one last one. I have one more. Okay. Let's do a molarity calculation. We have 481.6 grams of magnesium nitrate. And it tells me that that many grams per liter would result in an overall density of the solution being 1.114 grams per mil. And it wants to know what the molarity is. So you need to get moles of solute and then liters of solution. So pause the video and give it a try. All right, are you ready? Well, we know that 1 liter of this solution has this many grams. So I'm going to take that number of grams, convert from grams to moles, and I find out that I have 3.247 moles of solute per liter. Well, wait a second. Isn't molarity moles per liter? So I'm all done. What number did I not use? I did not use that density, did I? It was just extra. That drives people bonkers. They will spend so much time freaking out trying to figure out where were they supposed to use density and you weren't. You don't need to use it. When you write out your units for what you're interested in, you will see that you don't need that conversion factor. It is super common to have more info than you need. Okay. So my best advice, right? Write out your units. Think about your desired unit in terms of a numerator and a denominator. Try to get the numerator converted. Try to get the denominator converted. Put them back together. Don't stress out about extra numbers. And lots of practice. It has to become second nature that you know your pathways. Just like when we learn dimensional analysis. All right, everybody, that is it. I hope this was helpful. Bye.